Good afternoon. My name is Chris Elam. I'm the East Central Service Advisor for GA Larson. Today's course will be on Rheem air handlers. So we'll cover basically the standard air handlers, the PSC, the constant torque, and the ECM, non-communicating air handler. This is normally a 4-hour course, but due to the COVID restrictions, we're trying to condense these down to more manageable time. So we're going to condense this down to 2 hours, maybe a little bit less. So we'll cover installation, service, troubleshooting, and we'll start off with some identification and specifications of each of these units. If you do have any questions as we go along, you can go into the chat feature and I'll periodically take a look and see if anybody has put anything in the chat screen, and I'll try to respond accordingly. I've also included my name, my cell phone number, and email. So if you have any questions, feel free to call me, send me a text, send me an email. I'm happy to help you. So we'll get started here. Some of the features on the Rheem air handlers. This one here is the RH1T and 2T, but the features and specifications are pretty much the same. The compact design, all standard air handlers are 42.5 inches up to 57 inches. They do have a attractive pre-painted cabinet, rugged steel cabinet construction for strength and versatility. One good feature is it has a 1-inch foil-faced insulation that's mechanically retained in the blower compartment for sound and thermal performance. You do have 4-leg blower mount, which is important. Gives you a more rigid and stable mounting for your blower. Blower housing with controls, motor, and blower. Good feature. It's a slide-out design for easy service and maintenance. It does utilize the traditional open element design for heat pack applications. It is field convertible for vertical downflow, horizontal left, and horizontal right. So it's pretty versatile. It will come out of the box in an upflow position. Indoor coil design provides low air side pressure drop, high performance, and extremely compact size. The expansion valve on the indoor unit provides operation for both air conditioning and heating. So the coil will work for both heat pumps and air conditioning. The coils are constructed, they're all aluminum except for the copper braze fittings. These coils are tested at the factory with an extensive refrigerant leak check. Coils have copper sweat refrigerant connections, which is important. Big bonus here, they utilize the Chatlift metering device connections. So if you do have to replace a TXV, you basically have 3 bolt-on connections. Molded polymer corrosion resistant drain pan. It does come with duct flanges provided as a standard feature on these units. Provisions for field electrical connections available from either side or the top of the cabinet. We'll go over some nomenclature here so you kind of understand what you're getting. This is going to be your typical model number, just to kind of break this down. The first letter is the R. In this case here, it indicates the Rheem. The H stands for air handler. The 1 stands for the number of stages. In this case here, the T stands for constant torque motor. If you had a V, it's a variable speed. If you have a P, it's a PSC motor. Comes in whole capacity, so you have 2-ton, 3-ton, 4-ton, and 5-ton. In this case here, it's a 24,000. It's a 2-ton. We have 3 standard widths, which is 17.5, 21, and 24. Depending on the unit, there's 3 different efficiencies. You have a standard. This is a standard, the S, an M, which is the medium efficiency, and a high H, which is the high efficiency. The T here stands for TXV, TEV. You also have an E for an EEV, and you have a P for a piston. We don't stock any piston models. Everything we stock either has the TEVs or the EEVs. The A is the major series. In this case here, the N stands for non-communicating. If it was a communicating air handler, which we'll not cover today, but it would actually have a C. And here's your various voltages here. In this case here, it's listed an A, so this will be a 115 volt model. Normally what you'll see will be a J voltage, which is your 208, 240 single phase. Finally, the A stands for minor series. That doesn't really mean a whole lot to us in the field, but that's part of the model number. So if there's been any revisions, it would reflect that in the model number. Okay. Let me see here. There we go. Just trying to find the correct one to put up here. Okay. We're going to go over some applications and some installation. We'll go over clearances, vertical upflow, and horizontal applications, vertical downflow, and horizontal right applications. We'll also go over converting the air handler to horizontal right and vertical downflow. We'll discuss installation in an unconditioned space, as well as installation in mobile or manufactured homes. With the Rheem air handlers, they are approved for mobile or manufactured homes with a few small provisions. We'll go over the power wiring, grounding, control wiring, and we'll get into the TXV sensing, TXV troubleshooting towards the end of the course here. Clearances, they're designed for 0 inches of clearance to combustible materials. Electric heat requires 1 inch clearance to combustible material for the first 3 feet of the supply plenum and ductwork. Some units require a combustible floor depending on the heating kilowatts. The following table kind of shows where these fall into on the requirements. If installed in a downflow position, a combustible floor base, small riser box is required. Units with electrical heating kilowatts equal or less than the values listed in the table do not require a combustible base. Vertical units, clearance on at least one side of the unit for electrical connections. Horizontal, clearance on either top or bottom for electrical connections. Big one is refrigerant and condensate drain connections. They give you plenty of connections to use, depending on your application orientation, but you got to make sure that that the drain is installed properly, you have access, you have to install a trap, and you don't want to block the filter. You need a 24-inch minimum access to the front of the unit. That will give you plenty of access to get in there and service the unit. If you need to pull the blower wheel or blower housing to service the wheel, change the motor, or if you need to pull the coil. So don't box yourself in down the road if you have to perform service on it. This may be installed either in ventilated or non-ventilated spaces. The vertical upflow, which is going to fall into the RH1P, RH1T. Side return air opening. You must field fabricate a return air plenum with large enough opening to ensure proper airflow. And also a big one is strong enough to support the unit's weight. I come across one a long time ago, and it had actually buckled the box. It was still all hooked up, so that was a real treat to try to support the unit, take out the old broken box, put a new constructed box in there, and put it all back together again without having to unhook every single thing. Return air duct, install duct flush with the floor, use fireproof resilient gasket between the wood unit, set the unit on the floor over the opening. Now it is important, all these air handlers, as well as Rheem's gas furnaces, and most furnaces these days, it does not give you a provision for a filter. So you have to ensure that you, whatever kind of filter you want to use, preferably like a 4-inch media filter is best. You have to make sure that you allow for provisions to fit that filter in there, and you don't block that in with drain piping, refrigerant lines, or anything else. Vertical upflow, return air is to be ducted flush with the floor. There again, use the fireproof gasket between the duct unit and floor. Support along the length of the unit on all units installed horizontally. Do not support or suspend the unit from both ends without support in the center. If the unit is supported or suspended from the corners, run 2 reinforcing rails to support the center as well. If you're going to do a horizontal, secondary drain pan kits are required when the unit is configured for horizontal left position, really any position, if you're going to be over a finished ceiling or living space. Normally it's not a matter of if it's going to leak, it's a matter of when it's going to leak. You do not want to have a ceiling come down. I've seen too many of them do that. Somebody not putting pans in, not wiring the safeties up correctly, not wiring up safety at all, and then they're looking at replacing a whole ceiling or worse. These may be converted to horizontal right and vertical downflow. We'll go over some quick pictures showing you how to convert it to horizontal right flow. Like I said, out of the box, it's all set up for an upflow. Step 1, remove the screws from the lower panel that is covering the evaporator coil. Remove that panel. Remove the 2 screws holding the evaporator coil in place. At that point, you can use the frame of the evaporator, slide the coil out of the cabinet. It does tell you do not use the evaporator coil as a handle. It's aluminum, even if it's copper. If you try to start yanking on that, you could and may very well break that. So use the actual frame itself. The unit is supplied with an extra set of coil rails that will need to be attached to the cabinet. They are smart enough here. They actually give you some dimple holes here on the side where to mount these rails. Use a drill. It tells you an 1/8-inch metal cutting drill bit. Drill through each of the dimples. When finished drilling, sweep away any metal chips. Attach the coil rails using the specified sheet metal screws. The shorter of the 2 rails is mounted on the right side of the cabinet. This is to accommodate the location of the drain pan fittings. Lay the air handler on its right-hand side so the evaporator coil compartment is now on the left. Be careful not to damage the cabinet. Slide the evaporator coil back into the cabinet. Make sure that the rail on the right, kind of see right here, is fully engaged with the cabinet rail. Once it's in there, secure the evaporator coil with 2 screws. Reattach the front panel. Remove the screws from the panel covering the blower assembly. Oh, let me back up here. Kind of jumped ahead. Yep. So secure the evaporator coil with 2 screws. Reattach the panel. You're good to go. So as you're converting the air handler to the horizontal right, reattach the front panel before moving the position to its final position. Remove the screws. This is for the vertical downflow here. Remove the screws from the lower panel that is covering the evaporator coil. Remove that panel. Remove the 2 screws holding it in place. There again, use the frame, not the actual piping, to pull it out. The unit is supplied with an extra set of rails. There again, you do see the dimples that you need to screw into or drill into. Once you make those drill holes, to protect the low voltage wiring and strain relief located at the top of the air handler, place styrofoam packing down here at the bottom so it doesn't cause any damage. Turn the air handler 180 degrees so the coil compartment is now on top of the blower compartment. Attach the coil rails using the supplied sheet metal screws. The shorter of the 2 rails is mounted on the left side of the cabinet. This is to accommodate the location of the drain pan fittings. Slide the evaporator coil back into the cabinet. Make sure that the rail on the right side is fully engaged. Reattach the front panel. You're good to go. When you're installing a unit in an unconditioned space, be it a crawl space, attic, there's a few provisions for that. The exterior cabinet has a greater risk of sweating when installed in an unconditioned space, primarily due to temperature moving through the air handler and the air circulating around the unit. Duct sizing and airflow are critical and based on the equipment selected. If other than factory flanges are used, the attachment of ducting must be insulated to prevent sweating. If a full perimeter supply duct is used, it's the responsibility of the installer to provide duct flanges as needed to secure and seal the duct. All wire penetrations to be sealed. In some cases, the entire air handler can be wrapped with insulation. As required, use a secondary drain pan that will protect the structure from excessive sweating or restricted coil drain. If a heater kit is installed, be sure the breaker or disconnect cover is tightly sealed to the door panel. Now here's the instructions on mobile homes. I get calls all the time, guys asking if they're approved. Yes, they are approved with a few provisions. They must be secured to the structure using L bracket or pipe strap. You still must have a minimum 24 front clearance. It is important the air handler is secured against the wall. Secure the top of the air handler to the wall stud using a 2 16-gauge thick angle brackets, 1 on each side. Attach brackets with a number 10 self-tapping half-inch screw to the air handler. Lag screws to the 1.5-inch wall stud. Secure the bottom of the unit with 2 16-gauge L brackets, number 10 self-tapping half-inch screws, and use 5/16 lag screws half-inch to the floor. Since it's a mobile home, it's got to be secured and stable. Away from the wall, attach pipe strap to the top of the unit, number 10.5 long self-tapping screws on both sides. Angle the strap down away from the back of the air handler, remove all the slack, and fasten to the wall. Again, using 5/16 lag screws, 1.5-inch long. Secure the bottom of the unit, 2 16-gauge L brackets with the number 10 to the air handler using 5/16 lag screws, 1/2-inch to the floor. Power wiring, like I say, generally, what we see is the 208, 230 models. So you got to make sure that proper electrical power is available for connection to this unit. If required, install a branch circuit disconnect It is important to have the safety disconnect handy. Important, after the heater is installed, electric heat, units may be equipped with 1, 2, or 3 30 or 60 amp circuit breakers. These breakers protect the internal wiring in the event of a short circuit and serve as a disconnect. So it's basically a double service. They will protect the unit, but they'll also serve as a safety disconnect. The circuit breakers installed within the unit do not provide overcurrent protection of the supply wiring and therefore may be size larger than the branch circuit protection. So it is important, you use the proper sizing, make sure your connections are secure and tight. If they are not secure and they're loose, you'll actually start overheating your breakers and you'll start getting some breaker trips. Supply circuit power wiring must be 75 degrees Celsius minimum copper only. Do not use aluminum. Power wire may be connected either to the right, left, or top, whichever is convenient. Power wiring is connected to the terminal block in the unit control compartment. Grounding, important. Class 2 low voltage wire should not be run in conduit with power wiring, must be run separate from power wiring unless class 1 power wiring rating is used. It's a good idea not to mix those because you can get some noise interference, especially if you're dealing with the communicating system. These particular air handlers are not. Low voltage control wiring should be 18 gauge, no lengths longer than 100 feet. 16 gauge wire, anything longer than 100 feet, 16 gauge wire should be used. Don't use speaker wire. Don't use that really thin, cheap thermostat wire. Use the proper 18 gauge solid wire. Low voltage control connections are made to low voltage pigtails extending from the top of the air handler. They've tried to make it as easy as possible for you. Color-coded, the pigtails to connect to. They made it fairly simple. Connections for control wiring are to be made with wire nuts. Make sure separation of control wiring and power wiring has been maintained. Grounding may be accomplished by grounding metal conduit when installed in accordance with electrical codes to the unit cabinet. Grounding may also be accomplished by attaching ground wires to ground lugs provided in the unit wiring compartment. Ground lugs are located close to the wire entrance on the left side upflow. Lugs may be moved to marked locations near wire entrance on the right or upflow if alternate connection is needed. Use of multiple supply circuits require grounding of each circuit to the unit. So if you have 2 power wires coming here, you got to make sure that you actually ground both those circuits. We'll get into the TXB towards the end here. We'll go over the RH1P. So this is your single stage PSC air handler. Kind of go over some components here. So the basic component overview, they're all going to be pretty much the same for the most part in an air handler. Pretty simplistic. You've got your blower, time delay board. You've got your low voltage connections, pigtail. You've got your 24-volt transformer. In this case here, you have a multi-speed PSC blower motor, and you have a evaporator coil. The blower time delay board, it does contain a 3 amp fuse. One thing to be aware of, if you blow that fuse during installation, what will happen is your fan will kick on and it will never shut off. It will just keep running and running and running when you have all your wires hooked up, your low voltage connections made. It's kind of weird that it does that. It has people chasing down rabbit holes as to what the problem is. I've had guys replace, inside wire, outside wire, you name it. If you come across a motor that's acting kind of funny, it's just running, check the fuse first. Literally takes, 2 seconds to do that. If you find your fuse is blown, obviously replace it. You may have made some connections, or you may have hooked something up wrong, then turned the power on. So just remember that. This little board here controls the blower motor during operation and both heating and cooling. It's powered by your 24-volt transformer. Has a built-in 30-second blower off delay when cooling ends. When a call for supplemental extra heat ends, the blower off delay is increased to 45 seconds. Receives commands from the thermostat at the 5-pin connection right here. That's where your pigtails are. And 24 volt that feeds the R comes from the time delay board. The 4-pin here is going to be for our auxiliary heat. Blower motor is connected to the time delay relay via the black relay right here, motor terminals right here. Blower motor comes from the factory preset to run at high speed with the motor's black high-speed wire connected to the motor speed terminal. For low motor blower speed, connect the red motor lead in place of the black. The 4-pin plug here is used only if you're using auxiliary heat. If you're doing just a cooling only air handler, this will not be used. There again, it has a 3-amp fuse. Has a 24-volt VA, 208, 240 multi-tap primary. So depending on whether you're using 208 or 230, you'll want to configure it as such. This factory configured at 240 volts. If you're down to 208, make sure you move your terminal to the 208 terminal. Testing the transformer is pretty simple. If you have power to the unit, you want to check on the low side, the step down side here. If it's powered up and you do not have 24 volts there, you could have a bad transformer. But there again, you would want to check on the top to make sure that you have 240 into it. If you have 208, 230 in, you should have 24 out. But you can go a step further with that. You can also ohm out your transformer. So if you're questioning your primary side, disconnect the power first. Don't do this live. Test your primary side of the transformer, whatever voltage you're using. Once you do that, the meter should read approximately 75 ohms. If there is no reading, the primary winding is open. As long as you have approximately 75 ohms, it's a good transformer, a good primary. If it's open, replace the transformer. If voltage is present at the primary but not at the secondary, remove power to the air handler, remove one lead from the primary and one lead from the secondary of the transformer. If the primary winding checks out good, next connect the test leads of the meter to the secondary side of the transformer. The secondary side should read much lower. The secondary side, you should read about approximately 1 ohm or so. If you have the approximate 1 ohm, your secondary is good. If there is no reading on the secondary, you have a bad secondary side of your transformer. This is the aluminum evaporator coil with the factory installed TEV, horizontal condensate drain pan included. These are aluminum coil. They're rated for 410A refrigerant. They have pre-installed thermostatic expansion valves. And if you look right here, mentioned earlier, they're using the chat-lift connections on your expansion valves. There's no braze required. So if you do have to replace a thermostat expansion valve, you basically have 3 bolt connections right here. So that makes life a whole lot easier. Has a built-in horizontal drain pan and it does ship with 2 additional coil mounts, coil rail mounts, so you can convert them to horizontal right. When you're adjusting the blower speeds, and we'll get further into this later on, especially with the constant torque and the ECM, these units require indoor air volume to be proper, and we'll get into static pressure later. But by setting the air volume CFM to the limits, and table below here, the indoor blower will potentially move enough heat to ensure the evaporator coil boils off the proper amount of refrigerant. So the tables here will tell you, like a case here, 675 CFM, 600 CFM, 549. One thing to understand, if the CFM in air is too low, the evaporator will flood and hold refrigerant. The outdoor coil will not receive enough gas, which causes it to starve. The subcooling is now off and capacity will be low. If the heat flow is too high, the evaporator coil boils off a lot of refrigerant and will overheat the compressor. So it is important. We'll kind of dig into this a little bit, but airflow is very critical. That will affect your charge on the heat pump side or air conditioning side as well. It'll affect the comfort. It will affect everything. When you're adjusting blower speeds on the EC or PSC, the 2-speed blower motor that is factory shipped is already set for the high speed. The performance data table below will kind of give us an idea of what we're looking at here. The airflow chart will indicate the delivered air volume at a given external static pressure for both high and low. So if you come down here, this is telling you no heater. Come over here in low speed here. It's saying see 0.4 static pressure, about 562 CFM is what we can expect. And if we go into high speed here, at a given CFM, we have to, at a higher static, we need a higher speed. So if we're at 0.7 and we're in high speed, where we pushing about, looks to be about 599. So it kind of gets different when you get into the ECMs and the constant torques, but it is important that you read your static pressure, understand that. At that point, you can actually set your blower speeds accordingly. So we'll talk about a little bit about measuring static pressure. Look at static pressure like your blood pressure. If you have high blood pressure, it's not good for your body. You're slowly wearing yourself out, little by little. So think about that when you think about static pressure. As long as you have a manometer, a couple pitot tubes, and some rubber hose, you can learn to take the proper pressure readings. So we'll kind of break this down here. Locate a position on the supply air plenum where a hole can be drilled. Drill a 1/4-inch hole. You have your little pitot tubes here, which are specifically for reading static pressure. Insert the static pressure tip that is connected to the high port of your dual manometer to the positive side of your digital manometer. Probe tip should be pointed so the airflow hits the tip of the tip of the probe. That will have a little effect on that. So that's going to test our high side. Now we're going to go into a position on the return side. There again, drill a 1/4-inch hole. Then we're going to install a second pitot tube. And we're going to install that either on the low port or the negative side of a digital manometer. Probe should be pointed so that the airflow hits the probe directly. Call for cooling. You can really check it in any speed, but what you're looking for is worst case scenario, honestly. So call for cooling, which should be your highest speed. Read, oops, kind of jumped ahead there. Yeah, read the external static pressure that's given on the static pressure gauge. If the static pressure is above, is 5.5 or above, reference the performance table for the air handler. At that point, you can use either the high speed, but your static pressure is going to tell you basically how your system's breathing. This gets real important with X13s and ECMs, because as that static pressure goes high, it really one's the max. As you start going above 1, you really start killing that unit. I know when I used to sell variable speeds, you know, years ago, variable speed motors would solve any problem known to man. Some people loved them, said it's great, you know, I'm saving money. Other people said, well, it's loud as can be. You know, my electric bills actually went up. So that's the thing with ECMs and constant torques. If they're running appropriately and they're not overworking, they will save you money. They are quiet. I didn't know that then, I mean, years ago. But, you know, those systems that the customers weren't happy was because the static pressure was way out of whack. So kind of pay attention to this. It's a real easy to do. I used to do them on just about every single call, because if you do this on a regular basis, you can actually identify problems for customers that they don't know they have. Or maybe they're experiencing something, but they don't know why they're experiencing it, or they're just used to it. Or if you have a customer that you've had to replace multiple motors for, you know, maybe do a static pressure reading. Because a lot of things will go right back to airflow. So in this case here, if the measured static pressure is below 5, you can go ahead and drop down to the red, the low speed tap. If necessary, repeat the measurements and reference low speed motor tap data on the chart. Upon the completion of this process, seal up the holes. You can use whatever you want to, little silver tape, those little snap-in divots, whatever you need to do. If the airflow is too low, below 5.1 and the high-speed blower tap is being used, make sure the supply voltage on the air handler is 240. If the voltage is 208, make sure that the blower is set to the yellow motor lead. If the wiring is correct, the total external static pressure across the air handler must be reduced. When external static pressure is too high, the external static pressure across the air handler is generated by air flowing through components such as grills, filters, registers, dampers. Static pressure is also due to turbulence caused by air turning in ducts that, you know, turn right off the top of the air handler. The last thing that generates static pressure is ducting, is friction from air scrubbing inside the surfaces of ducting, flex duct, you know, anything that can cause restrictions. One thing that's huge is when you're testing these, you know, you want to make sure that all the ducts are open as well. They're not using those crazy cheap 1-inch filters that, you know, save the world. Those are more restricted right out of the gate than, you know, practically anything. The static pressure across the air handler due to obstructions, turbulence, and friction make it difficult for the blower wheel to cut the air as it spins. As the motor works to turn the blower wheel, the motor rotor begins to slip in the revolving magnetic field of the windings. The motor slip causes the blower wheel RPM to actually drop and the CFM to drop. So by reducing the static pressure, the motor will experience less slip and the RPM of the blower will increase. So ironically, you can keep ramping that motor up, keep restricting it. You'll actually cause your airflow to drop. That's even more pronounced with the constant torques and the ECMs. If you really want to, this is kind of an important formula to remember. You can use different flow hoods and wherever you want to calculate your airflow, but a simple way to check your airflow, especially out of a air handler, which we're talking about, is this simple procedure right here. It will give you your CFM. It's your BTU output, volts times amps times 3.14 divided by temperature rise and your constant. So we'll come over here. In this case here, we multiply the voltage times the amps in our example.
We're not crazy.
243 volts. 243 volts times 43 amps.
Okay.
Multiplied to determine the BTU output. You'll have 10,449 times 3.414, which will give you 35,673 BTU output.
For salad?
Determine the temperature rise by subtracting the supply air temperatures from the return air temperature. So you have a 109 minus 73, which gives you 36. Multiply the temperature rise by your ACF. 36 times 108 equals 39. Divide that. You know you're operating at 915 CFM. If that's where you need to be, then you're perfectly fine. If you're not, then you need to make some provisions to adjust that.
Pretty dang close, yeah. I got like one more little salad. I can wait till tomorrow if you want. That time.
Hey, Keith, can you hear me? That's why I tell him to mute that there.
I'm sorry, can I hear you?
Yeah, can you hear me?
Yeah, was I messing you up?
Well, yeah, I could hear you, and it was kind of throwing me off a little bit. Could you?
Sorry, I thought I had it on mute. I apologize.
That's okay. Thanks. Okay. I'll have to get back to where I was now. There we go. We'll get into the RH1T. This is the single stage with using the constant torque. A lot of people like these because they will increase the efficiency of both your heat pump and your air conditioning. You have a little more control because you have up to 5 speeds on this, which will accommodate a lot and save you some issues. We'll kind of go over through some of the components, slightly different. Not the end of the world, but there are some different features on here. So the blower time delay, transformer, low voltage connection pigtails. In this case here, you're using the constant torque blower motor, which is basically a pre-programmed ECM motor. So you're getting kind of the benefits of an ECM motor electrically and control-wise, but you're not having to spend all the extra money for it. And you've got the aluminum evaporator coil here. A little bit different blower board here. You still got your 3 amp fuse. In this case here, you have a 6-pin connection. 4-pin for your auxiliary heat. And if you look down here, you'll see where it says X13. These are your motor connections down here. So you don't have the big huge relay. You have motor connections right here. And these are going to be 24-volt connections. The constant torque blower is connected via the time delay board via the three connections. X13 common, that's your common. X13 speed, SPD, which is going to be your heating, cooling, fan speed. And then you have an X13G, which is basically 50% of your constant fan speed. So not quite an ECM, but you get some of the same benefits. Blower motor comes from the factory, preset to run on high torque, which is T5 motor connection when energizing the X13 speed. And that is important. There again, you have the same transformer, 24-volt secondary, 40 VA, 208 or 240. Factory configured for 240 volts. There again, you have the same aluminum evaporator coil with the factory installed TEV. Unfortunately, I had I guess you'd say the pleasure of troubleshooting the very first X13 motor in Indianapolis. It was on a Bryant unit, and it wasn't that old. I didn't sell it, but I had to come out and fix it. Nobody had really explained what the X13 was up until that point. So I had to figure out what it was and figure out how to troubleshoot it. And then come to find out they didn't even have the part in the company. Didn't even have it, a way to order it. So they're actually super easy to troubleshoot, though. That's the good thing. If you're going to troubleshoot these, basically turn the power off to the air handler, disconnect the low voltage wire Y that goes to the outdoor unit, remove the L, the black, and the N, neutral, your orange line, leads from the motor, power on the air handler, and you're checking for 208, 240 between L and N. This should be a constant power, the 208 or 240. If you have that power, your line sight is good. So if it's not present, obviously you got another issue to resolve on that. So at this point, you can call for cooling mode. You're going to check for 24 volts between common, which is the X13 COM, and the motor speed X13 SPD terminals here. If 24 volts is not present, the control board is defective. Because as soon as you put it in cooling, you should get 24 volts at those two terminals. That's what actually turns on your blower. So if that's not there, replace the control board. 24 volts is present and the motor will not run. Obviously check the connections here. Also check the connections at the motor and the board. And if the connections are secure, the motor is defective. Replace the motor. If the motor is defective, it must be replaced by a direct OEM replacement or an approved OEM replacement for warranty. All constant torque motors are factory programmed specifically for each air handler. And make sure you can reconnect your Y wire when the repair is complete. So this kind of comes into play with any X13 motor. Your line voltage, whether it's a furnace or air handler, your line voltage is always present. You're looking for the 24 volt signal to turn on and command the motor and to run at what speed. So if the 24 volts is there, bad motor. If it's not there, bad board. Now we'll get into the RH1Vs. This is your true variable, not constant torque. Very nice units. They have a little bit different features on the board. When I sold units, I always loved to sell variable, regardless of what it was. It's just a much better unit, more electrically efficient. Once you learn the static pressure, and you can make those provisions to not cause those problems, you can utilize these variable speed furnaces to your benefit and make the customer completely happy. If a customer has a variable speed furnace air handler in their home and it's a good installation, airflow's good, you know, that's what they'll get used to. That's what they'll always want. So one thing about this, you're looking for premium efficiency. They're again aluminum coils, high static capable, constant volume blower, return air entry via the bottom of the air handler, 24-volt non-communicating systems only. So it gets all the variable features, but you don't have the communication. There again, it's available in hole sizes, 24, 36, 48, and 60. And these are the constant volume ECM blowers. Available voltages include 208, 230, single phase. Component overview. There again, you'll notice the board is different. Board, you have the constant blower ECM. You got your transformer, low voltage connection pigtail, and your coil. Now here's you can see the board is distinctly different. This is your blower time delay. Once again, it has 3 amp fuse built in. Controls the blower operation during heating and cooling operation. It's powered by the 24-volt transformer. Receives commands from the thermostat at the 9-pin right here, connected at the right-hand side. The 24-volt that feeds the red wire comes from the time delay board. The constant volume ECM motor connected to the time delay board is the 16-pin right here. The blower speeds and functions are controlled by this connector as well. Line voltage required to run the blower comes from the separate line voltage plug located on the motor module. You'll see you have a series of dip switches down here as well. You will have some LED lights on here. Since this is a non-communicating, the LEDs will kind of give you an idea of what's going on. LED will flash to indicate the desired programmed CFM requested by the 8 dip switch settings. It'll flash one time for every 100 CFM of programmed airflow. If the airflow is not a multiple of 100 CFM, the last flash will be a very brief to indicate the program request is below the 100. For example, 6 flashes and a brief flash indicate a request of greater than 600, but less than 700. Flashed CFM volume is an indication of what has been programmed into the switches. If the requested CFM, not the actual CFM. There again, you do have the 4-pin connection right here. That's going to be if you're using accessory auxiliary heat. And we'll go over the dip switches right here. You have the various dip switches. Switch 1 and 2. That's your cooling airflow settings. Switch 3 and 4. That's your cooling airflow adjustment. That lets you tweak that a little bit, fine tune that. 5 and 6 is your heating airflow selections. 7, 8 is your cooling delay profiles. And then number 9 and 10 is your on-demand dehumidification, whether it's active or passive. So this particular motor here kind of gives you a good shot of the side of the motor, the board connections. It's a variable speed, constant volume motor, 3-phase motor with a control module. That's what the end bell right here is. Advanced programming capability, along with enough power to operate up to 1 inch of static pressure. Modules are not interchangeable between different air handlers. Module commands the motor to operate at a determined RPM based upon the program inside the module. Lower than desired RPM due to high static pressure, the module will increase the power delivered to the motor and attempt to get to that RPM and reach that correct speed. Should the module reach maximum output, without achieving that desired RPM, the module will momentarily overload and stop power to the unit. There again, the static pressure is so important on these. If I'm selling furnaces now in the field, first thing I'm doing is I'm doing a static pressure on the duct system before I sell the job. That way I can tell ahead of time, you know, hopefully you have a working blower motor. But if you can check that, you can say, okay, do I have a static issue? If you do, present that on the sale. You know, you'll number one, you'll be different than anybody else. You may be higher, but you're going to correct a problem. You want to explain to the customer, you know, hey, if I put this in for you, this is going to happen. You know, if they don't want to heed your warning, I guarantee you nobody else will. And then when a new furnace is put in, if they're not happy with it, chances are they're going to call you. But it's much easier to sell ductwork up front than try to sell it after the fact. I run into that all the time. It's hard to justify you just sold the customer the premium system, and now you have to spend more for ductwork because, you know, you didn't check it. So you have two plug connections, one for line voltage and the other is for the 16-pin harness connecting to the motor control board. So your single pin is going to be your line voltage. There again, that should always be live. If you do not have 208 or 230 to that, then you have to determine why that is. This is always live. Controlled by dip switches on the blower control board located in the air handler. The airflow performance data can be referenced to determine the CFM at a given external static pressure. That's very important. Just because you think that you have it set to a certain speed, if you don't know your static pressure, you just have it set at a certain range. You don't really know what you're putting out unless you, number one, check your static pressure, or number two, do the airflow calculation. At that point, you can know exactly what you're putting out. But that is very important because we're not just selling furnaces, you know, a heater and an AC anymore. We're selling some pretty sophisticated systems. People are spending, I saw one the other day, it was like almost 30 grand that was sold. It had every bell and whistle and then some. People are spending a premium for these systems. You know, take the time, make sure they're getting what they're paying for. Because if not, you're going to get callbacks and callbacks and callbacks and callbacks. And every single callback that you make on a system eats into whatever profit that you made. How the constant volume responds to the control board request. The 16-pin harness carries the requested airflow information to the motor module. The module will determine the proper RPM. The motor module will monitor that RPM of the blower motor shaft. Should the blower motor RPM be lower than required, the module will increase the current flow to the three-phase motor and attempt to get the RPM to the correct level. Should the current required exceed the limit, the motor will reduce current to prevent damage. If this happens, the CFM delivered by the constant volume motor will not reach the CFM. In some cases, they'll actually slow down to protect themselves. I know I personally blew my own motor because I had supposedly a 1-year filter. It's not a 1 year. I changed it every 6 months now, but my wife kept saying I can hear the furnace sounds different. The furnace sounds different, and of course basically I took it way out of its range because the filter was so dirty. And then on the coldest night a couple of years ago, it went out. So I should have known better, but I didn't do it. Okay, testing the constant volume ECM motor. Required tools, multimeter to check your line voltage, and you really should have a TechMate Pro or a Zebra, or a Supco makes one. I know we had them on sale this spring for like 60, 65 bucks that had both harnesses. So you could test the 16 pins and then the newer models as well. I mean, there's no excuse not to have an ECM tester now. It's just so easy. So all you need, number one, is to check your line voltage. Do you have 240, 208, 230 to black and orange? If you do, you're good to go. Next, you want to do this when its power's off, by the way, as well. Unplug your 16-pin connector. Plug the TechMate in to the 16-pin connector. Connect the TechMate 2 alligator clips to R and C for 24 volts. At that point, turn the switch on. So at this point here, your TechMate is actually powering it up. Okay, so if you turn the system on, it should run. If the motor runs, the problem is either with the wiring, which is likely doubtful, or you have a bad board that's not sending 24 volts. If the motor does not run, the motor, more than likely it's the module that's defective. If the module is defective, if they're warranty, I think you get the whole motor in the module. That's how it usually is, but you can replace just the module on these as well, if the motor's good. And I've only seen a handful, maybe 6 motors that were truly defective. Every other time it's been the module. But there's a way you can check the motor as well. Testing the motor, you can take the module off. 2 screws will hold that module off. You'll have a little retainer ring around here. Pop that off. Take your pin connector out of here. Then you'll actually remove the module. Set it to the side. At that point, using an ohm meter, you've got 3 wires here. L1, L2, L2 to L3, and L1 to L3. So you're going to ohm out each combination. The measured resistance between all motor leads should be equal to or within 10% of each other. If any motor lead resistance combination is infinite or the readings are not equal, you'll usually see one way off. Replace the motor and the module. If the resistances are correct, go to the next step. At this point, you're going to check basically going from each pin to ground. The resistance of each motor lead to the motor chassis should typically be infinite. If any of the motor leads read lower than 100,000 ohms, the motor is defective and must be replaced along with the module. If the motor checks out good, you can replace just the module. There again, you do have the 24-volt transformer, aluminum evaporator coil with the chat lift connections on your EXTEV. Okay, I'll tell you what, let's take a 5 to 6 minute break here. Then we'll pick back up, say, at 4:10. Then we'll pick back up here. Thank you. Okay, we'll go ahead and start back here now. We'll get back into the heat packs. Kind of gives you an overview picture of the standard heat pack. We're going to go over the component overview as well as the kit installation. You have your standard open air elements right here. You have your electrical sequencers right here. Depending on the number of elements that you have, that will dictate how many sequencers you have, as well as breakers. In this case here, you have basically 2 elements. You've got 2 safety limits here. Got your circuit breakers, and you have your control voltage with the 4-pin plug for your board. So you'll take this plug that into your board. These are resistive type heaters. 208, 230 line voltage. They are isolated. They will not touch. They can break eventually if you get them hot enough over a period of time. Extremely low airflow will cause that, but you'll probably get the call beforehand with poor heat. Powered by the electrical heat resistor sequencers. They do have auto reset safety limits. They will reset many times, but eventually they will open up. The safety limits, they protect the heaters from over temperature due to low airflow. Take your pick: dirty filters, blocked off returns, anything that will cause overheating. I had a guy one time, he had a ranch house, and it was kind of a unique house, but he was trying to force more air to one side of his house. So he actually took like plastic bags, filled them with towels, and stuffed them in all his registers on the one side of the house. Bad for him because he actually burned his heat kit up. Good for me, ultimately ended up costing him several $100s, but he went about it the wrong way and it cost him a bunch of money. This is your control voltage harness. 5-pin connector connects to the board. Low voltage energizes from the thermostat circuit, will energize your blower motor and the sequencers. The harness carries the low voltage signal from the control board and sends it directly to the sequencers. You have your built-in circuit breakers here. The circuit breaker is correct size to protect the heater accessory from overcurrent. Used in addition to the circuit breaker in your panel. Electrical leads that connect to the circuit breaker into the line voltage circuit of the air handler. Do be sure that the connections on the factory side are secure and tight, as well as when you're installing your line side. Make sure they are good and they are tight. If not, they will create heat eventually and actually cause this breaker to trip. It'll trip more than likely a few times, but you can actually cause that breaker to melt. Your sequencers, they switch the line voltage power to the resistance heaters, powered by 24-volt coils via the 5-pin harness. When powered by 24 volts, they start a time delay period. That way you're not bringing on all those elements at one time. So once it's energized, it starts a timing period. After the first timing period ends, it'll kick one sequencer in, then another, then another, then another. You'll also have the same reverse cycle. So when you lose the call for heat, it starts a downtime cycle. So once one element will clear, another, another, and another. And you can actually, if you put your amp meter on your line voltage side, excuse me, you can actually watch that happen. You can actually watch each element drop out or pop in as they engage. To install one of the kits, they've actually made it pretty simple. Normally, you're not going to be hooked up yet, but you could be hooked up if you're replacing one. Turn the power off to the unit. Remove the screws that holds the electrical panel on. So if it's a brand new unit, you're going to have this blank off plate right here. Remove that blank off plate. At that point, you can place the heater kit through the opening. Once you get that kind of in there, it's not terribly difficult. If you line your screws up, it will be in there safe and secure. I used the 2 screws retained earlier from the blank off plate to attach your breaker plate there, and then clip the circuit breaker onto the circuit breaker bracket. If you've got more than one, clip those in as well. This is a big one here. I've had guys call me before, like, I've got this red and black wire. Where do they go to? You'll have 2 pigtails coming off the breaker here, a red and a black. it is imperative here that you tag those in. At the top right hand side, you'll have your orange and black from your motor right here, and you'll have 2 empty spaces on top. The red from the breaker should go to the orange, and the black from the breaker should go to the black. Connect the high voltage ground wire to either the ground lug on the bulkhead of the air handler or the ground lug on the heater kit. Remove the 2 screws covering the electric cover box. Remove the cover and then connect the 4-pin plug of the heater kit to the board right here. Reinstall the enclosure, making sure the 2 screws will not pinch the wires. That's kind of a trick sometimes, but if you kind of jockey that around a little bit, you can get the wires safely into the right side. There's a hole cut out there. You can get that plate back on. At that point, you want to remove the knockouts, the amount of knockouts that you need on the blower panel to accommodate the number of circuit breakers that pertains to your heat kit. Clean the surface around that. The surface must be clean and dry, free of grease and oil. And it actually comes to this nice little cover right here. So peel off the release paper on the back, and then you can install your breaker cover. That'll keep people from actually getting to the breaker with their bare hands. Align the breaker cover over the knockout, press firmly for 30 seconds, and it should be stable. At that point, you can replace the blower panel back on, making sure the circuit breaker is aligned with the knockout on the panel cover. Those actually aren't very difficult. You can usually install those kits rather simply. Once you're done, restore the power back on. Now, what I would tell you, if you're installing one, you know, obviously if you're installing a heat pump air handler, check your heat pump, make sure it's working okay. But as a byproduct, you also want to, number one, check your emergency heat, the heat elements by themselves. Now, what I would do is I put my meter on there. I'm checking amp draw on however many elements I got. I want to watch, number one, that they're engaging, and then I want to make sure that each element kicks on. Then I want to make sure each element kicks off. And then as a byproduct of that, if I'm using a heat pump, I want to bring in my heat pump, and then I want to kick in the auxiliary heat with it. So then I'll have both the heat pump and the emergency or the auxiliary heat, and I want to use my meter to verify each element comes on, each element comes off. They make it pretty simple. Do that on startup. If you do that, it'll save you lots of trouble. I've had guys, even my own installers, I had to kind of train them to do that operation, because invariably something would be wrong, and then I get the call back and, you know, emergency heat's not on or auxiliary heat's not working. If you're testing your heat limit switches, all you really need is an ohm meter. So if you look right here, you've got, this is 2 elements. So you got the beginning element on the left and the element on the right. So you can actually ohm from one side to the other. That will actually give you your ohm reading for the whole element. So if you're reading continuity all the way through that, you have a valid complete element. Now, if you're going to check the heat kit limit switch, basically you're going to check at the bottom here, set it on ohms reading with no power on, and then you're going to check from one side of the limit to the other side of the limit. You know, if a reading of 0 ohms indicates that the limit switch is closed, which is what you're wanting. If the limit switch is good. If that limit switch is open, that switch is bad. So you've got some airflow issues to work on to figure out why you're overheating. Dirty filters, closed off vents, you know, the list goes on. this is huge. Why air volume must be established within the required range. The air volume that an air handler or gas furnace delivers will have an operational effect on the heating and cooling mechanical cycles, also comfort, noise. You can put the best furnace in the world in if it's not set up properly, and customer's going to start complaining on day one. Also, the air volume level will also affect how the duct system delivers air to the individual zones. When air volume is too low, air diffusers will not work properly. Notice the throw of the air. If the boot is receiving 100 CFM, the air throw is not high enough to actually hit the ceiling. In this case, the 411 is not a good choice. This is using the Hart and Cooley chart here. It won't give you enough throw to hit the ceiling. Some mechanical problems related to low air volume, low capacity, liquid flood back to the compressor, low superheat, and subcooling levels. You can also have some TXV hunting issues, and a bigger one is potential oil return problems. That's going to cause you wear and tear on your outdoor unit. Achieving rated air volume is critical for proper operation of the air termination diffusers to basically throw the air where it needs to go to. Depending on where they're located, they have to be able to throw and distribute to the whole room. It's imperative for proper operation of the mechanical heating and cooling systems. Improper air will result in mechanical failure and room temperature controls. As you get into inverter systems and variable speed and inverter systems, it is super critical. You'll just open yourself up to all kinds of failures that will ultimately have to be resolved before the issues go away. Duct pressure. When a fan is hooked up to a duct system and is operating, the fan attempts to move air down the ducting path. The energy required to move the air will blow back against the fan. The more the air fan tries to move through the ducting, the more energy is required. The energy required to move air down the path is static pressure energy. Ducts that have the largest resistance to airflow actually blow back more energy to the fan source. So it kind of gives you a little idea here. The straight up is nice and smooth. This one right here, it's actually going up and down, side to side. You want it to be a nice, smooth path. The amount of energy required to move air through a duct path will depend on the dimensions, duct, surface, turbulence. If the duct path is too restrictive, the energy required to move the air will be high, which is going to increase power consumption. Along with power consumption comes noise. Also will be comfort issues. If the duct path is open and smooth and very limited components for the air to pass through, the energy required to move that air will be low. That's what when you sell at variable speed, that's what you're selling. Comfort, noise, kind of a smooth, easy comfort. So that's where if your duct is restricted, it's going to cause you all kinds of issues and increased power consumption. So blowers consist of blower motor, wheel, housing. The blower motor uses electrical energy to turn the wheel. The blower wheel converts the electrical energy into static pressure and velocity pressure. Every system has a blower curve that plots how many CFM of indoor air fan can deliver at a given static pressure. So if we come down here to this one, we're going to say just pick 0.5. So if we're at high speed, you know, our CFM is 433, and high speed on high is 655. But if we take that same high speed and increase our static to 0.7, now instead of getting 655, we're getting 549. So we're actually getting less airflow, but we're consuming more energy and making our motor work even harder. The reduction in CFM as external static pressure rises is caused by the blower slipping in the airstream as static pressure rises. Sometimes you can actually hear almost like a pulsing, I guess the way to look at it. In the right application, you can almost hear it. It sounds like it's pulsing. The blower motor will fall off the torque curve, and the motor RPM will increase without an increase in airflow. So you're actually motor spinning faster, but there's no increase in airflow. X13s have an internal control module that will increase the electrical current flow to the motor as the external static pressure increases. This increased current potential of the motor is limited. So that's, you can push these motors pretty far. Once you push them to a certain point, they'll either what they call fold back, or they'll actually start reducing speed to protect themselves, or in some cases they'll actually fold back. They can actually cut in half to where you think you're at a certain RPM or a certain speed, but it will not let you operate that, and it'll actually cut it in half. So in this case here, the 5-speed motor, we will go to speed tap 3. So at 0.5, we're actually at 808. If we go to 0.70, we're at 584. Now, if we increase that up to 0.9, you can just see it's just going to keep on reducing. Not only is it going to reduce, but it's also going to cost your customer more money. And chances are it's going to be significantly louder right out of the box because of that high static pressure. Constant volume motors, your constant volume ECMs, are capable of delivering air rated at an air volume at an external static as high as 1. I've seen them run as high as 1.5, and then also what they call unknown. So you're basically killing your motor. You're making it work triple time, consuming more power than it's supposed to, and you will shorten the life of it. It's variable speed 3-phase motors controlled by a replaceable module. The module will run at programmed RPM levels that are programmed into the motor control dip switches. So we'll just come over here and say we'll go to 3.5 ton. So at 0.1, we're pushing 1379. Yeah, that's actually not bad. If we go to 1.0, we're at 1305. It's not terrible. Usually it's a little more dramatic than that, but you do actually increase your power consumption, and your airflow will reduce. If RPM falls below the required level, the module will increase the airflow to increase power to the windings. Should the external pressure get too high, the motor module will reach maximum current and will reduce current. It will slow down. At high static pressures, these motors will run very hot. And they will burn a large amount of electricity. It could be the difference of 2.5 amps, 3 amps on operation. If it's a nice, smooth, low static situation, you could take that up to 9 amps. That much difference. And actually, even though you're running at 9 amps and that motor's working triple time, you're not getting nearly the airflow you should. In fact, you're basically burning up the system. At that point, customers will complain because they're going to be super, super loud, and chances are they're not going to be comfortable. It will affect the comfort of the home. Component pressure drops. It's important to know what's going on. Components that are in the duct systems, evaporator coils, if they get dirty, return air filters if they're too restrictive, supply air registers, a bunch of them shut off or not enough. If you have takeoff or balancing dampers, if they're not opened, return air grills. I've seen them taped off. You may not have enough. All these components will have natural pressure drops that are published in a perfect system. Kind of gives you an idea. As air that turns or merges with other air in duct systems, you create turbulence, resistance to flow. Now, this is a kind of a poor example here. This would be a perfect application for horribly high duct system. Horribly high static, right out of the cabinet. You're going up 10 inches and turning hard. That's going to create excessively high static pressure. Now, it is important. Get guys to call me all the time. Once they determine they have high static, like the EcoNets, if you deal with a communicating system, it will tell you. There's a way you can actually view what your static pressure is. And it's fairly accurate within maybe a point or two. So if it tells you it's high, you can bet it's high. So at that point, you need to determine whether it's the supply issue that's the problem or the return issue that's the problem. So what you want to do is with the air handler or furnace working, you can they're showing the Magna Helix, but you can use a dual port manometer. Put one in our pre-drilled supply and one right here in the coil, right here. So you're actually measuring both of them. Leave the system on at this point. Remove the probe out of the supply. Okay. Now we've dropped down to 0.22. Not at the end of the world. That's pretty decent. So that's on our return side. Now we'll change that around. So now we'll put the supply probe back in, pull this one out. Now we see where our high static is, 0.4. So we know we've got some issues on our supply side. That's what's causing the energy consumption, the noise, comfort issues. So at that point, you want to find out what's causing that. If could be as simple as a bunch of vents shut off, vents blocked. I mean, you name it. But once you find out find out which side of the system it's on, find out the culprit, and then resolve it. If the problem is in the supply duct and the evaporator coil is sitting on top of it, you can measure the static drop across the coil. Now those are also published in the spec books, so it will tell you exactly what it is, if it's a dry coil or a wet coil. That also will tell you if it's dirty. If you do a pressure drop across that, it'll tell you if it's what your drop is and if it's dirty, and that's a real possibility. Tips for reducing component pressure drops. Study component pressure drop tables. Match the lowest pressure drop coils to the gas furnace cabinets. Select high efficiency filters that have pressure and MERV ratings drops rated at 492 feet per minute or higher. Select filters that offer the lowest static pressure drops for the CFM being chosen. Pick larger filters, 4-inch, 5-inch, and use transitions to the filters to slow air down. Use quality supply air registers. In some cases, it's there in the house. You can't really do anything about it. But, if you're starting from scratch, use the proper supply air registers. Buy manual D and study the duct fitting group data. Learn duct layout, and you'll start to, as you come across things, you'll start to see mistakes and issues from previous installations and ways to resolve that. Extend plenums deep on downflow furnace and air handler applications. That goes as well for an upflow. You know, you don't want a 6-inch plenum before you take a hard takeoff. Reduce friction in ducting. This is a good one. Stretch all flex duct to max compression of 4%. You don't want a bunch of sagging spaghetti flex duct. And also you got to learn to size the flex duct according to what you're truly wanting to achieve. I've seen lots of guys, if they're going to run 6-inch vents, but then they're going to do flex duct. Well, run the same 6-inch vents. The flex duct, it's reduced, so you have to upsize that to accommodate exactly what airflow you're wanting to get. We'll cover a little bit of TXV here. The TEV metering device should maintain a constant suction vapor superheat level when the air conditioning system has proper air levels. Low levels can cause the TEV to hunt back and forth as it tries to maintain a steady superheat. Subcooling is operating at the required level as indicated on the outdoor unit nameplate. Flashing of the liquid refrigerant prior to the entrance of the TEV can lead to high superheat levels. Couple things to take in effect here. Verify your liquid line is properly sized and within proper length and line limits, lift limits. Excessive pressure drop can cause loss of subcooling at the TEV. The refrigerant may flash prior to the TEV. You could have excessive superheat that would be likely. The suction pressure drop between the outdoor coil and the indoor coil are within 3 psig on R22 or 5 on R410A. If the pressure drop is excessive, the suction vapor superheat will be higher than it is at the exit of the evaporator coil. If all the above conditions are met, the TEV should be able to reduce or increase the size to compensate for changes in the indoor heat load and changes in the outdoor air temperature. The measured suction vapor superheat range should be about 10 degrees Fahrenheit up to 20 degrees during normal operation. Now, with TEVs, expansion valves, they have enough problems on their own, but proper installation practices, brazing, flowing nitrogen as you're brazing, not overheating things, will save you a ton of problems down the road. Excessive heat during installation can cause damage to the valves. If the sensing bulb is on the refrigerant line during brazing, it will affect the levels in the TEV bulb. The sensing bulb pressure is an opening force and may be enough to damage the push rods in the TEV. So, seeing guys do it, you know, it's not a good practice. If this happens, the valve will remain in the always full open position. Should the valve become jammed open and stays there, the valve will have to be replaced. Now here's what we typically, or some combination of it, with the valve sticks closed. The sensing bulb pressure is in an opening pressure. The pressure pushes against the equalizer line pressure and internal spring pressure. The position of the TEV internal orifice will be determined by the difference in the opening and closing pressures. If that sensing bulb loses refrigerant charge, the spring under the TEV metering device will push up and close the valve. The valve will need to be replaced if the sensing bulb loses its charge. It can, and it definitely happens. A lot of times it's self-inflicted, the expansion valve problems, but if your bulb loses the charge, that's where you're going to start up, and it's just your refrigerator's going to hit a brick wall. It's not going to flow through that expansion valve. But there's a couple ways to check this. Number one, obviously, you can tell by running the system, but there's another further way you can do it. What you're going to need is refrigeration gauges, temperature probe, and a glass ice water. Remove the bulb from the suction line. Call for cooling. With the outdoor running, measure suction pressure, suction line temp at the outdoor unit. With the unit running, so you kind of have an idea what it's doing, loosen the sensing bulb from the clamp and place it in a glass of ice water. The water should immediately cause that valve to close. I mean, it may be possible to hear the refrigerant flow decrease because it should be so dramatic. Decrease in refrigerant flow is an indication that the valve is in fact working. To verify that, go outside and look at your suction pressure and temperature again. The suction pressure should fall and the suction vapor superheat should rise. This indicates that the valve is closing. You can also do that again if you want to open it up. You can put it in a glass of warm water, or you can hold it in your hand, or any combination. But if you heat it up, it's going to open it. If you're going to put it in ice water, it's going to close it. But as you do this, you should see wild fluctuations. If you see very minor fluctuations, then you probably have a defective TEV. Okay. Well, that is it for the Rheem air handlers for today. I do appreciate your time. And if you have any questions or any concerns or comments, please feel free to give me a call, send me a text message, send me an email. And we do appreciate that you attending our training. Thank you very much.